Welcome to Lesson 2.5, Data Classification. In this lesson, we'll see how to use Matlab to perform data classification tasks. Classification is one of the most common data analysis tasks. It involves the use of one or more features or measurements of a process to attempt to determine what type of process is occurring. For example, perhaps our data are recordings from sensors of a manufacturing robot on an assembly line, and we'd like to have a program that classifies the robot as being healthy or in need of maintenance based on the sensor recordings. Or perhaps we have a speech recognition program running on a smartphone that translates the user's words into commands and needs to interpret the features of the audio signals to reliably classify the audio commands. Sometimes classification accuracy is high stakes. For example, tech entrepreneur Elon Musk is a well-known multitasker running multiple businesses with the automobile manufacturing company Tesla and the space exploration company SpaceX. It's probably critical for his speech recognition method to correctly classify the phrase tire and sprocket as opposed to the phrase fire the rocket. Another way to think of classification is trying to figure out how to partition the feature space such that any vector that falls within a certain partition of the feature space belongs to a specific class. For example, consider two samples of a two-class process. In this example, we measure two features for each sample, and so the features of each sample can be displayed on a two-dimensional scatter plot. We can visualize the classification for each point by displaying them using different colors and symbols. The task of classification would be to find some partition of this feature space that separates the two classes. Thus, we would classify feature points that fall to the right of this line as belonging to the blue circles class, and to the left of this line as belonging to the red X's class. In this lesson, we will go to Matlab and look at some examples of classification problems. We will use progressively more sophisticated data classification methods, and you will learn about strengths and weaknesses of commonly used classification approaches. Let's get started. Fisher's iris dataset is a classic example dataset for classification. We have 4 features in our feature set, and each data point is classified in terms of species. Let's start by looking at a scatter plot of the first 2 features. First for the first species, then the same for the second species, with green circles, and the third species with blue asterisks. We can label our axes. And put in a legend. Okay, so we can see our 3 classes, which is our 3 species, being plotted as a function of the first 2 feature values. Our goal is to come up with an iris classifier that will take as input values for these 2 features for a specific sample and output the class that the sample belongs to. Let's create a function to do this. We will call it my iris classifier. it will input a feature vector and output 1, 2, or 3 for the class that the data belongs to. So how will this function work? Let's run with the idea of partitioning the feature space. For example, we can see in the plot that most of the data points for species 3, Virginica, have value for feature 1 greater than 6. Otherwise, if feature 1 is less than 6, most data points with feature 2 greater than 3 belong to Setosa. Otherwise, in the bottom left corner of the plot, most data points belong to the second species. Repeating what we just stated by looking at the plot in code, what we have is if the value of feature 1 is greater than 6, we're likely to belong to class 3. Otherwise, if feature 2 has value greater than 3, we're likely to belong to class 1. Otherwise, we're likely to belong to class 2. This works if we have just one feature sample as input, but what if we would like to classify many feature samples simultaneously using this function? Assuming that is the case, we can initialize our class output as a vector of zeros that has the same number of rows as our input feature matrix. And then in a for loop, we can loop over the rows of the feature matrix and classify each sample on each ith row of the feature matrix independently. There. We've just created a function that partitions the feature space and can be used to classify data based on features. Let's take a look at how we can visualize this partition function on this 2D plot. We can do this for arbitrarily complex classification functions by sampling data points uniformly across the feature space using the mesh grid function. Then we can classify each of those grid locations using our classification function. We define our uniform sampling grid using mesh grid to range from 4 to 8 in step sizes of 0.01 for feature 1 and 2 to 4.5 in steps of 0.01 for feature 2. Then we can simply supply that list of feature space coordinates to our classifier and get a classification output for every grid point. Next, we want to use the contour function to display what we call the decision boundary between each class for our classifier. The contour function requires a 2D matrix as an input to create the 2D contour. So we reshape our classification output vector CLS to be the size of our input X matrix. Then we can draw the contours. The first contour will be representing the decision boundary for class 1. The third argument, input to contour, is the grid of values. The fourth argument says we should be drawing the contour at the interface where the grid points have a value of 1. So by supplying a classification grid that is equal to 1 at locations classified as class 1 and 0 otherwise, a contour drawn at an interface value of 1 will be a contour that wraps around the foreground grid points corresponding to class 1 and separating those grid points from those locations not corresponding to class 1. The first two arguments in contour tell the function the xy coordinate locations of the grid points specified in the third argument. And we can draw this contour as dashed lines. Next, we can draw a similar contour for the decision boundary between class 2 and other classes with green dashed lines, and then class 3 and other classes with blue dashed lines. As we can see, our classifier segments our feature space into 3 sections, each corresponding to one species of iris. While this is indeed a legitimate classifier, it's not a particularly effective one. We can see many data points do not fall in the correct segment of the classifier space. We can easily quantify the accuracy of the classifier. If we use our classifier to classify our data set using the feature values in mesh, we can count how many out of the 150 data points are classified correctly. How many data points are classified correctly will be the sum of CLS equal to S divided by the length of S times 100 to give us the percentage of accurately classified entries in the data set. We can see our ad hoc classifier gives us 74% accuracy. For some applications, that may be good. However, I think everyone can see from our scatter plot that it is fairly easy to do better. For example, there are several false positives and false negatives for class 1, and class 1 could be pretty easily separated from the other 2 classes using a diagonal line. Further, while class 2 and 3 have lots of overlap in the first 2 features, we saw in the lesson on dimensionality reduction that principal component analysis can help to capture the directions of greatest variance in multidimensional datasets and help make the data more easily separable. So let's try the PCA method and see if we can improve our classifier. First, let's compute the PCA feature space coordinates. And plot the first 2 PCA dimensions as we did in the previous lesson. First, the PCA coordinates for species 1 in the first 2 PCA features. Then the same for species 2 with green circles, and species 3 with blue asterisks. On the x-axis we have PCA feature 1, and on the y-axis we have PCA feature 2. Now we can create a new classifier function similar to our first one that is based on our PCA features instead of the original features. Just like before, our goal is to delineate the feature space, but this time for our PCA features. For class 1, this is an easier problem now because PCA has well separated class 1 from the other classes. So we can define a data point as belonging to class 1 if the value of the first PCA feature is less than minus 1.5. For classes 2 and 3, a vertical line does not do a good job of separating the two classes. However, we can define a diagonal line to separate the two. We can imagine a line passing through our plot right about here that should work well. On this line, when feature 1 is 0, we should have a value for feature 2 of about minus 1.5. So let's set b equal to minus 1.5. When feature 1 is equal to 2, our line should have a value for feature 2 of about 0.5. So we rise from minus 1.5 to 0.5 over a run from 0 to 2. So our line has a slope of 1, and we can set variable m equal to 1. Now we have what we need to define a line using the standard line equation y equals mx plus b. So if we want to classify a new feature point using the values for feature 1 and 2, we can compute m times the value of feature 1 plus b and if we find the result is greater than the value of feature 2, we know the data point falls below this line in the plot, and the data point should be classified as class 3. On the other hand, if the result is less than the value of feature 2, the data point falls above the line, and the data point belongs to class 2. Okay, let's use our classifier to delineate our PCA feature space. We again use mesh grid to define a 2D grid of data points across the first 2 dimensions of our feature space. We'll vary feature 1 from minus 4 to 4 in step sizes of 0.01, and feature 2 from minus 2 to 2 in step sizes of 0.01. Then we pass those values through our classifier, we reshape the resulting vector to match the size of our grid. Then we can use the contour function to delineate the 3 class regions. red for class 1, green for class 2, and blue for class 3. We see we successfully defined our vertical line at minus 1.5, separating class 1 from the others. We also have our diagonal line that does not perfectly separate classes 2 and 3, but is pretty close. So, how good of a job does our classifier do? Remember, we can quantify its accuracy. We pass our data points through our classifier. Again, our data points are our PCA space features. And see what percentage of cases does the result equal the true iris identification stored in S. We find we have accuracy of 96%. That's not too shabby. Using PCA to transform our feature space so that most of the variance is captured in the first 2 dimensions, we can easily delineate the feature space with high accuracy. Now we have seen a couple of examples of creating ad hoc classifier functions. That is, we have handcrafted our partitions in our feature space through visualization of the data. But instead of handcrafting our classifier, are there methods available to automatically partition the feature space? The answer is yes. In fact, there are far too many methods to cover in this introduction. However, we will look at a few examples of classical classification methods that can be easily implemented in Matlab. There are 2 general categories of classification methods, referred to as supervised versus unsupervised machine learning methods. The distinction arises in the training data the method uses to determine the partition. Supervised methods are trained with a data set that includes exemplars with both feature values and known classification. The method then aims to partition the feature space in a way that separates the known classes. Unsupervised methods are trained with exemplars with feature values but without known classification. The methods aim to find partitions that result in distinct clusters of data points in the feature space. If the data tend to cluster for different classes, the resulting partition can be used as a classifier. One of the most popular and simplest unsupervised learning methods is called k-means clustering. The method partitions the space by finding the centroid of k clusters of data points, where k is an input parameter to tell the algorithm how many clusters to find. For example, let's go to Matlab and look at our scatter plot of 3 classes of irises. Let's plot our data in a new figure. Now we can try out k-means. The k-means algorithm in Matlab is stochastic, meaning it relies on randomly generated numbers. Thus, to ensure our results are reproducible, we need to explicitly seed the random number generator. We can do this with the command rng. We provide the method our first 2 PCA features. And since we have 3 classes of irises, we can choose k is equal to 3. The method assigns each data point to a cluster, numbered 1, 2, or 3, in an output CLS. It also provides the centroid, or mean, of each of the 3 found clusters. And the second output we call big C. To classify a new data point, we need only find which one of the three centroids that the data point is closest to in the feature space and assign the data point to the corresponding class. Here we plot the three centroids with black circles. We can find the distance from each point in our mesh grid that we've defined with big X and big Y. Recall the equation for Euclidean distance is the square root of the sum of squared differences across each dimension. So the distance to centroid 1, called dists1, is equal to the square root of C, first row, first column, minus X, quantity squared, plus the same squared difference for the second feature dimension, C, first row, second column, minus Y, quantity squared. To find the distances from the grid points to the second centroid, termed dists2, we use the same line of code, except we use the second row of C for the second centroid. Similarly, dists3 will use the third centroid. Now, to classify each grid point, we find which data points have values for dists3 smaller than dists1 and dists3 smaller than dists2. Those we can define as being class 3. Then for data points where class 3 is equal to 0 and dists2 less than dists1, that will define our class 2. And finally, class 1 is defined wherever class 2 and class 3 are both equal to 0. Then we can use contour to delineate our feature space as we have previously. So even without using class labels for training, K-means does a pretty decent job at separating the groups based solely on the distribution of the points in the feature space. Let's see how accurate this result is as a classifier. "31% accuracy? That's not right. We can see from the plot we're doing better than that. So what's the problem? K-means is indeed separating the data points into three classes. However, it's not assigning the same numeric label to classes 1, 2, and 3 that we are. CLS is the class label from K-means, and S is our species label. We can see the two are different. We can correct this by sorting out which new label belongs to which old one. Side by side, we can see that K-means class 3 corresponds to our class 1. K-means class 2 corresponds to our class 2. and k-means class 1 must correspond to our class 3. So the classes are reversed. We can reverse the k-means class labels by simply computing 4 minus the current label. 4 minus 1 is equal to 3, so class 1 will turn into 3. 4 minus 2 is 2, so 2 stays the same. And 4 minus 3 is 1, so class 3 turns into class 1. Then we can see our classification accuracy is over 88%. That's pretty good, considering the classes were not provided to the training process for the classifier. Supervised learning is different. If we have a dataset available with known classes, it makes sense that the learning process can benefit from being provided those known classification labels to improve classifier accuracy. This is supervised learning. Ultimately, the philosophy of supervised learning methods is twofold. First, we find the features for a new testing data point and can see where it falls in the feature space. Next, we define a metric of closeness to the data distribution for each class in the training data. Finally, we can classify a new data point as belonging to whichever class has a data distribution learned in training that it is closest to. K-means unsupervised learning has a direct supervised correlate. If instead of being blinded to the underlying classification, we know the true classes of the data, then we can compute the mean of each class and use those means rather than the k-means for classification. In this case, our metric for closeness to a data distribution is the Euclidean distance to the mean of the distribution. Let's see what happens when we do this. Let's first compute the mean of each class and plot them on a figure. The means for each class can be found by computing the mean of our PCA features for the first species, followed by the mean of our features for the second species, followed by the mean for our third species. We can replot our scatter plot relatively quickly using the up arrow to recall previous plot commands. And we can plot our new means using magenta circles. At this point, we've found our means in the variable c without needing to use the k-means function. So we can simply repeat all of the code we used previously for k-means in order to plot the new classification partition. First, we find the distances to the three means. Then we can determine classifications for our grid points. And contour the results. We haven't classified our data points yet, so we don't know exactly how accurate this partition is yet. To do that, for each data point, we need to find which of the three means that it's closest to. For this, we need to compute distances from each data point to each mean. Our first is going to be dist1, which is going to be the square root of two terms. First, we take the difference between the x-coordinate of the first mean and our PCA first feature, quantity squared. And the second is the y-coordinate of the first mean minus our second PCA feature, quantity squared. Distance to our second mean is the same, but in reference to the second row of our means matrix, and dist 3 to our third mean. Now we can define our class 1, 2, and 3 similarly to before for our data points. And the overall classification vector is 3 times class 3 plus 2 times class 2 plus class 1. And our accuracy compared to our species vector S is over 92%. So we can see when we use the means of the actual classes instead of the k-means, our classification accuracy increases slightly to over 92%. There are a range of options to define our metric on closeness to the training data distribution. We just used distance to the mean, but we can do better than a simple proximity to a data mean. If we assume our data in each class follow an n-dimensional normal Gaussian distribution, then we can account for the variance of each feature as well as the covariance between features. This is precisely what principal components analysis, or PCA, does, which is fit an n-dimensional Gaussian to a data set. And once we do this, we can use an existing metric on distance to a Gaussian distribution called Mahalanobis distance. Let's look at this conceptually before looking at a Matlab example. Consider these 3 classes of training data along with a new data point that we wish to classify. In our previous example, we would compute the distance to the mean of the 3 classes and use the closest distance as our metric. Now we can consider the training set as samples of 2D Gaussian distributions. By using PCA to fit a Gaussian to each class, we can draw a contour showing a distance of 2 standard deviations to the mean for each Gaussian. That's shown with these black dashed lines that are tight around the distributions. We can also find the Mahalanobis distance, that is, how many standard deviations away from the mean the data point lies to each class. That's represented with these wider contours with color code corresponding to each class. We can see that the new data point lies 18 standard deviations away from the mean of the red class distribution. Next, compared to the blue class, we have a Mahalanobis distance of 7.4. Finally, we see our new data point has a Mahalanobis distance of 5.5 to the green class. Our classifier would thus classify our new point as belonging to the green class since it has the lowest Mahalanobis distance to that distribution. Let's look at an example in Matlab to see how this works. First, this time let's make a function to fit PCA models to our data set. I'm going to call it myFitPCA. It will have 2 inputs, the matrix containing the training feature data D, and the vector of data classifications called class. The output will be a PCA classification model, or MDL for short. Within this function, the first thing we want to do is figure out how many classes there are, because we're going to perform PCA on the data for each class. The unique function gives us a list of the unique entries or variables in the class vector. And the number of different classes is equal to the length of this class labels vector. Next, we will have a for loop iterating for loop variable I from 1 to the number of classes. For each class, we will perform a PCA on the portion of the data set that corresponds to class I. This gives us our eigenvectors, eigenvalues, and data mean, which is conventionally labeled with the Greek letter mu for this class. And we store these results in our output variable. And finish our for loop and return. Let's try it out. I'm going to call the function on the command line with the inputs being the first two columns of our PCA features and the second input, our species label S. The first time we run it, I want to step through the function line by line, so I'll set a breakpoint here at the function entry point. After executing the first line, we can see class labels contains a list of the different classes, 1, 2, and 3, giving us a total of 3 classes. Next, we perform PCA on the portion of the data set where the class is equal to 1, and we get our eigenvector matrix, eigenvalues, and mu. In the next iteration, we get the same quantities for class 2. And in the final iteration, the same quantities for class 3. In the command window, the function returns the variable MDL, which is a struct containing 3 classes. We can visualize the shape of each PCA model by directly visualizing an isocontour for a specific Mahalanobis distance from each PCA model. As these data are 2D, an isocontour of constant Mahalanobis distance will be the shape of an ellipse. For an ellipse corresponding to a Mahalanobis distance of 2, representing 2 standard deviations from the mean of the model, we define an ellipse with centroid at the model mean. So we can define the x and y coordinates of the centroid like this, using mu. Further, its major axis orientation is defined by the principal eigenvector of the model in the first row of eigenvectors. And the major axis radius is equal to 2 times the square root of the corresponding eigenvalue. Similarly, for the y-coordinates of the major axis, we use the y-coordinates of the eigenvectors. And similarly, the minor axis direction can be defined using the second eigenvector and eigenvalue. With the three classes in our data set, the centroid, major axis, and minor axis are as shown here. In fact, just like a circle, which is fully defined by a centroid and a radius, an ellipse is fully defined by a centroid and the major and minor axes. How do we draw an ellipse? Well, let's first remind ourselves how we would draw a circle based on centroid and radius in Matlab. First, we define a radius for the circle, set to be 2.5 here. Then, we densely sample a set of angles where we want to define xy coordinates along the circumference of the circle. These would be radians from 0 to 2 pi, sampled at a fine interval, such as steps of pi over 32. We can then use our trigonometric functions, cosine and sine, to convert polar coordinates theta along with radius r to xy coordinates by computing x equals r times cosine theta and y equals r times sine theta. With densely sampled data, the set of xy coordinates on the circle are also densely sampled. With dense enough sampling, when we connect those samples by line segments, the result is that by all appearances we are plotting a perfect circle. The same process can be used for plotting ellipses. If the radius in the x direction is r1 equal 2.4, and the radius in the y direction is r2 equals 1.2, we can compute x equals r1 times cosine theta and y equals r2 times sine theta. Then our result looks like this. But what if the x and y directions are not aligned with the major and minor axes? In the general case, the major and minor axes of the PCA model will not align with the x and y directions, but rather will be oblique to the Cartesian coordinate directions. In this case, we define a polar coordinate system for the ellipse with theta equals 0, corresponding to the positive end of the major axis. Theta equals pi over 2 corresponds to the positive direction of the minor axis. Theta equals pi corresponds to the negative direction of the major axis. And theta equal 3 pi over 2 corresponds to the negative direction of the minor axis. Other values of theta between these orthogonal directions, for example, theta equal pi over 4, corresponds to a mixture of the major and minor axis directions. What defines the proportion of each direction in the mixture? Our same trigonometric functions cosine theta and sine theta. So in this case, we can define our coordinates as x equals major axis x times cosine theta plus minor axis x times sine theta. And y equals major axis y times cosine theta plus minor axis y times sine theta. How does this relate back to our original ellipse? Does all of the same mathematics apply? For our original ellipse, the major axis is in the x direction, so major axis x equals r1 and major axis y equals 0. Similarly, the minor axis would be in the y direction, and minor axis x equals 0, and minor axis y equals r2. If this is the case, then our equations would simplify to x equals r1 times cosine theta plus 0 times sine theta, and y equals 0 times cosine theta plus r2 times sine theta, which is the same as our original simple ellipse. Thus, the simple ellipse is one instance of the more general ellipse with arbitrary major and minor axes. Okay, let's return to Matlab and plot our ellipses for our PCA models. First, we replot our scatter plot of our three classes. Next, we define our dense samples of theta, ranging from 0 to 2 pi, in step sizes of pi over 32. For each of our three classes, we define the major axis x coordinates, for the ith class, major axis y coordinates, minor axis x coordinates, minor axis y coordinates. One last thing we need to account for is the centroid of the ellipse. In our slide examples, the ellipse was always centered at the origin, but for these three classes, we can see that the centroid is generally not at the origin. So how do we shift or translate our ellipses to the correct location? We simply need to define the centroid of the ellipse using mu and we can add it to the x and y coordinates that we sample around the circumference of the ellipse. When we plot the centroid in the x direction plus cosine of theta times the major axis direction, x component, plus sine of theta times the minor axis direction, x component. Then repeat for the y direction. By choosing the centroid to be the mean of the corresponding PCA model that's basically fitting a Gaussian distribution, then adding it back to the ellipse, we translate the ellipse to be centered on the fitted Gaussian distribution. We can plot this result with a black dashed line and get results that look like this. We can see when we draw these ellipses at 2 standard deviations from the mean of the multidimensional Gaussian distribution fit to each class, we get an ellipse that well approximates the general shape of each of these 3 data distributions. Now we need code to take a trained PCA model and classify new data using it. If we have a new data point, we will need to find the Mahalanobis distance to each model in MDL, because we will classify the new data point as belonging to the class corresponding to the smallest Mahalanobis distance. So let's write our Mahalanobis distance function. Our function will look like this. We'll call it Mahalanobis distance. We will have as input a single PCA model and a single data point in a row vector, data. Our output will be the Mahalanobis distance, MD. First, we subtract the model mean from the data point. And then we project the model eigenvectors onto the demeaned data vector. This gives us model space coordinates for the data point in vector B. Next, we can compute the multiples of 1 standard deviation per eigenmode implied by the coordinates in B by dividing the absolute value of our shape space coordinates by the square root of the corresponding eigenvectors. Since the square root of the eigenvalue corresponds to 1 standard deviation from the mean along that eigenmode, this results in the multiple of standard deviations along each eigenmode. Finally, to combine the standard deviations across different dimensions into one multidimensional standard deviation, we compute the square root of the sum of the squares of this result to get a single number, which we'll store in MD, which will be our Mahalanobis distance. In other words, MD can be computed by computing the square root of the sum of the squared PCA coordinates, each divided by the eigenvalues in the model, which describe the variance in the model corresponding to each eigenvector. The final Mahalanobis distance tells us this data point lies MD standard deviations from the multidimensional normal distribution defined by the PCA model. Okay, let's try it. Let's look at a data point lying at data equals 1, 1.5. We can add it to our plot. We'll display it as a thick black X. To choose a class for this data point, let's compute the Mahalanobis distance to the first model and step through the function. We can see that we first compute our shape space coordinates in B. Next, we find how many standard deviations we are away from the mean for the shape space coordinates according to each eigenmode. We find that they are both quite large. One standard deviation is by definition a typical deviation. Two standard deviations represents the 95th percentile of a normal distribution. So these both are very large values. Finally, the Mahalanobis distance is the L2 norm of this vector, giving an overall standard deviation from the multidimensional Gaussian of almost 18. Okay, that was one example model. Now let's compute for each of the PCA models the Mahalanobis distance. We can see, as we saw in the slides, that for this data point, we find a Mahalanobis distance for class 1, the red class, of 18. So the data point lies roughly 18 standard deviations from the mean of class 1. So there is a very low probability that it belongs to this class. On the other hand, for class 2, the green class, and class 3, the blue class, we find a Mahalanobis distance of 5.5 and 7.4. Both are somewhat low probability, but it is closer to class 2, so given that it must belong to one of these three classes, we choose class 2 as the most likely. Okay, so that's an example of how the classification should work. Now let's write the classification function. This one will be called myPredictPCA. It will take as input the class model struct MDL that we just trained using the myFitPCA, as well as a new data point or set of new data points that we wish to classify. Its output will be a vector containing the classification for each data point, as well as a score vector which will indicate Mahalanobis distance to the closest normal Gaussian distribution. The Mahalanobis distance represents how many multiples of one standard deviation from the mean does the data point lie from the mean of the normal distribution. Within the function, the first thing we do is figure out how many rows R are in the input data. This is how many data points we need to classify with our PCA classifier. After initializing our output class and score variables, we iterate over the R data points with iteration variable I. For each data point, we need to loop over the number of classes in MDL with variable j. Within each iteration, we find the Mahalanobis distance from data point I to the PCA model we've created for class j. After the for loop for j completes, we can compute the classification for data point I as belonging to the class that resulted in the minimum Mahalanobis distance to the class PCA model. We can do this using the min function. The minimum function first outputs the minimum value in MD score into score I, and then the index 1, 2, or 3 into the class I variable. So let's try it out. As before, we can classify each xy coordinate on our densely sampled grid. That we defined using mesh grid into variables x and y. And we can use the contour function where our third input will be our class output reshaped to the size of x. First for the first class, where that result is equal to 1. Then for the second class, where that result is equal to 2, we can show in green. And for the third class, in blue. So we can see this results in an excellent partitioning of our feature space. There are only a few data points that are not classified correctly using this partition. Why are they incorrect? Well, it's because the PCA distributions for classes 2 and 3 overlap. We can see this in our ellipse plots showing the isocontour corresponding to 2 standard deviations from the mean. For classes 2 and 3, these 2 ellipses overlap, showing there is a region where the data points have a similar likelihood of belonging to either class. Next, we can compute our classification error when classifying our input data set. We can see that our PCA fitting classification method results in accuracy over 97%. That's pretty good. Our myPredictPCA function and myFitPCA function were deliberately designed to mimic some of Matlab's built-in functions. Matlab's predict function takes as input a model and new data to be classified. There are a number of model types that work with predict. For example, a linear regression model can be created using fitlm. When we pass the resulting model to predict, with our feature points, the result is a floating point prediction of the class label number, which can be rounded to the closest integer for classification. We see that the linear regression results in accuracy of the input data of almost 97%. So that's almost as good as our PCA fitting method. Matlab also provides more sophisticated classification models for use with predict. For example, classification decision trees can be constructed using the fit-ctree function. A naive Bayes classification model can be constructed using the fit-cnb function. A number of other examples can be found in the Matlab help pages. All of these methods use very different formulations for classification, but programmatically they generally follow the same process. One, we build a classifier with training data using a fit function. And two, we supply that new data to the classifier to predict the class using the predict function. We'll look at one example, which is the support vector machine classification method. This is built into Matlab in the fit-csvm function. Support vector machines, or SVM for short, are one of the most popular traditional supervised machine learning methods, second to neural networks. SVM uses classified training data to partition the feature space. Using some clever mathematics, the partition separating the two classes does not have to be a simple plane, but rather SVM can compute a high-dimensional hyperplane separating the data. The result is that it is possible to obtain a decision contour that appears to be highly nonlinear in the feature space and has the freedom to perfectly classify the input data, no matter how much overlap there is among the points in the feature space, assuming that each data point in the training data feature space is assigned to a single class. Let's take a look at how this works. SVM only permits binary classification, so if we want to classify our three iris classes, we have to separate the classification tasks. Let's start by first separating class 2 from classes 1 and 3. We'll use fit-csvm. Our first input is our 150 by 4 feature matrix mesh, and the second input is the known classification for each data point. The output is the SVM model. We use predict to see how accurately the SVM model can classify the data we use to train it. We can see with default parameters, SVM tries to find a linear decision boundary, and we get an underwhelming accuracy of 74%. Let's try radial basis function kernels for SVM instead. These are what permit the high-dimensional decision boundaries. We tell the function we want to use RBF for the kernel function, where RBF stands for radial basis function. The precision of the boundary will be controlled by the kernel scale parameter. Where larger scales mean smoother decision boundaries, but sometimes finer scales are needed to accurately separate the classes. Even with a scale of 1, we get almost 99% accuracy. What about if we go down to 0.25? Now we have 100% accurate classification of the training data. Okay, so now it would be great if we could see what kind of decision boundaries support vector machines are coming up with. So far, we have fed it the full 4D feature set, but as we know, 4D data is difficult to visualize. So let's instead look at applying SVM to the first two dimensions of the PCA dimension reduced feature space. Oops, that was the wrong input. Let's try that again. There we are. So into predict, we input our model and the first two vectors in our feature set. So we can see with the default settings, we only achieve 69% accuracy. Now let's classify our grid points and plot our decision contour. Okay, and now our contour. In black. We'll also change the ISO value used to create the contour to 0.5 so that the contour falls directly between the grid points defined as belonging to class 2 versus not belonging to class 2. So plotting this decision contour, we can see why we only get 69% accuracy. There's no good linear boundary through this space that can separate the green data points from both the red and the blue ones. Okay, let's try the RBF kernel version. That gives much better accuracy of almost 97%. Now let's plot the decision boundary. We can see this decision boundary is highly nonlinear. It appears to encircle the green data points with a fairly smooth contour. Keeping that decision boundary smooth means a few data points are still classified incorrectly. How about going down to a kernel scale of 0.25? Here we get an accuracy of almost 99%. How about 0.1? There we get an accuracy of 100%. can see our magenta decision contour looks quite complicated. It's wrapped very tightly around the green data points. This demonstrates a very important concept for nonlinear classifiers, which is the idea of overfitting to the training data. With enough freedom in determining the decision boundary, SVM can come up with a very complex decision contour that works well on the training data, but will likely not generalize well to new unseen data points. Between these three different decision boundaries, the black dashed line likely represents the best balance between accuracy and generalization. The best way to evaluate the accuracy of a classifier is not how accurately it classifies data that are used as input for training, but rather how well it classifies new, unseen data that are not included in training. We call this a testing data set. Let's split our data into a training and a testing set. We'll have our training feature data in trained data containing the first two columns of every other row of DPCA, starting with the first row. The training data classes will correspond to the same rows of S2. Our test data will be the features in the remaining rows. Every other row starting at the second row. And the test data classes will be the corresponding rows of S2. So first let's fit an SVM with a kernel size of 0.1 to the training data. We can see that we can classify the training data with 100% accuracy. But when we apply it to the test data that have been held out, we can see our classifier is only 73% accurate, which is quite poor. So we have definitely overfit to the training data in this case. On the other hand, if we increase our kernel size to, say, 0.5, we're accurate on the training data 97% of the time. And also on the testing data 97% of the time. So this demonstrates how the right parameters are critical for avoiding overfitting to the training data. Matlab's SVM only lets us do binary classification. So how can we do multi-class classification with SVM? One way to do this is to create our own fit and predict functions that handle multiple classes. Let's start with the fit function. We'll call it myFitSVM. The inputs are the training feature data D in an n by m matrix, where n is the number of training data points and m is the number of features for each data point, followed by an n by 1 vector containing the classification in class for each input data point, followed by a scalar for the kernel scale to be used in the SVM RBF functions. The goal of our function is to compute a separate SVM model for each unique class label in the class vector and return all of these models in MDL. We start similarly to our myPCAFit function by using unique to determine the unique class labels in the class vector, and num classes will contain the number of different classes in the class vector, then in a for loop for each class, we define S, which is equal to 1 for data points where the class is equal to the ith entry in class labels, and 0 otherwise. Finally, we train an SVM to recognize this class versus all other classes. And store that in our output variable. So the final output contains a unique SVM classifier for each unique label in the class. Next, we write our predict function. My predict SVM takes as input the SVM models produced by my fit SVM, as well as an n by m matrix of data we would like to classify, containing n rows of data points, each of which are characterized by m features in the columns of the data matrix. The goal of the function is to find which of the models in MDL is the most likely for each data point to belong to. The result goes into an output classification class vector. Within the function, first, we find the size of the input data matrix. Then, for each SVM we have in MDL, we use Matlab's predict function and apply that SVM to the input data. The first output of predict is the binary classification. We're not going to use that here. The second output contains the raw model scores that the classification is based on. The magnitude of the score captures how far from the decision boundary the data point is located in the feature space. Scores greater than 0 indicate the data point lies in the background of the classifier, whereas scores less than 0 indicate the data point lies in the foreground of the classifier. So this number provides a way to compare the results of multiple classifiers. In general, a smaller, more negative score is indicative of a higher likelihood of belonging to a particular class. Thus, we compute a score for every data point for each model, and this goes into our score matrix. Which is R by number of SVM models in size. After the loop, we can use the min function to find with the score as input, to find the index to the minimum score along each row of the scores matrix. Since the min function finds the minimum along a column of the matrix, we transpose the score input matrix prior to computing the min. And since we don't need the value of the minimum, but rather just the index to the location of the minimum, we don't need the first input, and we only use the second input of the min function. The index to the location of the minimum implies the classification. That is, we're choosing the model that corresponds to the smallest or the most negative score for each data point. The output class will be a 1 by R vector, so we transpose it to be a R by 1, matching the row format of our data matrix. Okay, let's try it out. First, let's replot our data. Then we train our multi-class SVM model using our training data set, which contains half of our data points. The training data classes are every other entry in S, starting with the first one. Let's try out a kernel size of 0.75. Again, using our myFitSVM function. And first, let's look at the prediction accuracy on the training data. Which we can see is 96%. How about our test set accuracy? Our test set classifications are every other entry in S, starting with the second entry. And we find our prediction error in our test set to be about 97%. So we don't seem to have an overfitting issue. And let's look at our classification boundaries in our feature space. So we'll define a mesh grid as we've done before, except this time we're going to use a step size of 0.1. We pass those grid points through our SVM model. To obtain a classification. And use the contour function to display them. So if we use an ISO value of 1.5, that will show an ISO contour between classes 1 and 2. And an ISO contour of 2.5 will separate classes 2 and 3. So we can see that we obtain quite reasonable and smooth decision boundaries between our two classes. And that's with only using half of the displayed data points for training and holding the other half out for testing. To summarize, there are many different classification methods available for both unsupervised and supervised data classification, with supervised methods being the most straightforward and common. Across the very different supervised classification formulations, each follows the same programmatic process. First, we fit the classification model to the training data. Then the model is available to predict the classification for a new feature set. We also saw the trade-off between the complexity and freedom in the classification method versus the risk of overfitting the classification model to the training data. For example, linear regression models have little risk of overfitting to training data because the model is highly constrained. On the other hand, great care needs to be taken to have enough constraint on support vector machines to ensure a support vector machine model generalizes well and is not overfit to the training data. You now have experience with several powerful data classification methods and generally understand how classification methods can be trained and used in Matlab.